Continue. Today, today classes session to obtain the notes from Ellipse. It is based on paper by Prof. Dominic from Nottingham. Setting the we will have a snapshot. Request, press, just open for exercise. Setting the minimum UT gas chloride target using cascade analysis technique. So in this case, in this slide topic today, we explore about nitrogen integration, oxygen integration, or hydrogen integration. For oxygen integration, we will you also learn about purification and how to impart gas cascade table. So last week we learned about gas cascade analysis as well, but that is based on time base. Today this is based on the traditional gas cascade analysis, which is based on the stream and the process flow diagram. The typical process integration technique is resource conservation comprises two steps. First one is to set the minimum resource target. So minimum resource target is other name is the pinch, followed by the design of a resource conservation network to achieve the minimum resource target. The design you have learned not in gas cascade water, but still applicable because both is mass pinch analysis. The generic targeting technique applicable for various types of resource installation. Network include graphical composite curve and numerical targeting technique. This numerical targeting method is cascade analysis. We have three methods: limiting composite curve, sourcing system, and cascade analysis. Two key difference between synthesis problem of water and property-based network method of utility gas network. Differences between water pinch analysis and gas pinch analysis. First, while pure fresh water feed containing load, that is fresh water, has always been assumed to be available for synthesis of water network. It is quite common to encounter impure fresh feed for utility gas network, which is true. Yeah. So it's normally the feed for the utility gas network only within some percentage, 5% utilities. You get 99% with no utilities. You can be done, but expensive. Second, water network may consist of a mix of mass transfer based and non-mass transfer based process. Hence, the flow rate for water feeds the demand may not be fixed. However, this is not the case for utility gas network. Why? Because to maintain a steady state operation, in system pressure and this hydrogen reactor level, it is necessary to maintain a uniform inlet mass flow rate and gas concentration for gas consuming. So to maintain the steady state operation, so the inlet for gas should be stable. Nitrogen integration. Figure 1 shows the process flow diagram of a magnetic tape process. So the process starts with resin premixing and slowly premixing, dispersion, coating, drying, and filtration. So the pinch to the for this process flow will be done in this area, coating and drying. Explanation for the process coating ingredient. This is for magnetic tape manufacture. Coating ingredient are dissolved in organic solvent and form a slurry mixture. The slurry then suspended with resin binder and special additive. Next, the coating slurry is deposited on a base film. Liquid nitrogen is used, nitrogen gas is used to induce evaporation rate solvent with proper deposition here. A small amount of solvent is decomposed when it evaporates into other organic species in the coating chamber. The decomposed organic are then separated from the coating chamber exhaust gas using a membrane unit. The retented stream. So retented is because this membrane is cross flow membrane. So some of the inlet feed from the coating here will not pass through the membrane. So will be returned, not returned, will be pushed through the gaseous emission. Retented stream consisting mainly of nitrogen and laden with 1.98 with over percent organic solvent leave the membrane unit 3 kilogram. One. The coated film undergoes a drying process here, where nitrogen gas is used to evaporate the remaining solvent. So in this case, this nitrogen here, fresh feed. They didn't recycle it. So before we can recycle it, we need to know the minimum flow rate, which require pinch analysis. The drier exhaust gas here, F2, has a flow rate of 5.5 kg per second and solvent concentration of 0.4 watt%. The two exhaust gas streams are mixed and disposed of. So before we can start with pinch analysis, we need to identify the limiting data for sinks and source and understand the flowchart here. So coating and drying will require fresh feed nitrogen, and the excess nitrogen will be disposed. So this is also at the moment FD is 8.5 million per second. To reduce nitrogen consumption, it is proposed to reuse or recycle the solvent-laden exhaust gas to the cooking and drying processes, subject to the following constraints. For coating, the inlet for coating the nitrogen, if we were to recycle it, the flow rate should be within 3 to 3.2 kilograms per second, and the purity is 0 to 0.2%. For drying, it's much higher and much more pure pure fit up to 0.1%. So that recycle later, there are two stream here from membrane and drying. Can be recycled goes to nitrogen, but we don't know which one to be recycled. So later we need to find the pinch point. So from the pinch point, you can identify the percentage of the concentration. The outlet concentration for the coating and drying processes are assumed to be independent of the feed gas concentration. The constraint listed require the gaseous flow rate and its solvent concentration in the units to fall within this given range. Two key strategies to maximize reuse recycle. First, the maximum permissible inlet concentration should be assigned as the limiting concentration. While the minimum feed flow rate should be assigned as the limiting flow rate for each feed. Second, the source should be segregated into individual streams since mixing tends to degrade the source stream qualities. So from this second strategies here, meaning we have two streams of source. Maximum permissible inlet concentration, that one is referred back to this range. For this example, the solvent-laden exhaust gas should be segregated into membrane tank and dryer exhaust gas stream. The fresh makeup nitrogen is solvent-free and hence has a limiting concentration of 0%, which is pure nitrogen. The limiting data for the gas sink and surface are listed in table 1. Two sinks from drying water and source is from membrane retentate and from drying, or F1 and F2. So sink here refer to inlet. Refer back to the range. So for drying, it require minimum 5.5 kilograms per second of chlorine, and the maximum is 0.1%. For coating is minimum 3 highest concentration is 0.0.2. So this value here is refer back to the strategies. That's how they define the value. Cascade analysis technique. The first step in conducting GCA is to locate the various gassing and froth at their respective concentration level. As shown in table 2, the concentration level CK are arranged in an ascending order, and the flow rate of each gassing Fj and froth Fi, this one is CK, is located individually at its respective concentration level K in column 3 and 4. So based on the limiting data, table 1, this is table 2, so we need to rearrange the stream according to concentration. So 0, this one is feed, fresh feed for nitrogen. It's pure nitrogen, followed by zinc, 0.1%. Then zinc as well, 0.2, then phos 0.4. I just lost 1. So for if guessing and sourcing, I need to specify 5.53. Okay. Column 5, this column, we represent the net flow rate. Fi source minus C. Source minus C. Making source something at each concentration level K. Positive value indicate a surplus. Negative value indicate a deficit. So how? F1, Fi minus Fj. So 0 minus 5.5. So negative 5.5. And so on. The next GCA step is to cascade the net flow rate surplus or deficit down the concentration level to yield the cumulative surplus deficit flow rate FC shown in column 6. Why start with 0? Start with 0 normally for gas. That's why they say invisible gas cascade table, because we normally start with 0 FC. Then you do the cascade 0, 0 is 0, 0, 0. See here, 0, 0, 0, 0, minus 5.5, 5.5, minus 5.5, minus 5.3, minus 8.5, something like this. This is a cascade, zigzag. At the end, this is FD actually. So FD is 0. 0, the fresh nitrogen product is simply stage. To stage at this stage to facilitate the search for the minimum mobility gas flow. So the reason I do starting from 0 is to find the pinch point for this nitrogen integration. The cascade principle is conceptually explained in figure 2. This is what is cascade principle? In figure 2a, this figure, 50 kg per second of waste gas is available as a gas source at an impurity concentration of 5%. On the other hand, a gas sink exists at 100 kg per second here and can accept up to an impurity content of 10%. So in this case, here, wait, this case here, mentioned in the paper, the feed for nitrogen, fresh nitrogen, is 0%. But the requirement for that fresh feed, it can accept up to 10% relative concentration. So meaning some of the concentration for 5% here can be directed to this block diagram. Without considering, but without considering reuse, 50 kilogram per second of waste gas would have to be purged. In this case, just eliminate it. While 100 kilogram per second of fresh gas would have to be supplied to satisfy the sink. Remove 50 and then add fresh feed 100 kilograms. This is without nitrogen cascading. How about with cascading? By making use of 50 kg per second of the gas source, C equal to 5% concentration, to satisfy the gas sink that can tolerate a higher impurity of 10%, it is possible to avoid purging the gas source directly as emission. Doing so not only reduce not only the waste gas emission but also the fresh gas intake in both cases by 50 kilogram per second. So here, instead of purging the 50 kilogram per second directed to this box, but this box require 100 kilogram per. So another 50 coming from the fresh feed at 0%. But still, at the end, the concentration is 5%. Pretty. That is why we do cascade. The impurity load delta M shown in column 7 of table 2 is obtained from the product of cumulative. This is, we are still at cascading. This is the first table for gas cascade, which we started with 0 FC. So we need to calculate delta M, cumulative delta M, interval fresh flow rate, fresh gas flow rate FK, FFK. Cascading the impurity load down the concentration level of column 8 yield the cumulative load from the delta M. Finally, calculating the flow rate of fresh gas needed at each concentration level or the interval of fresh gas flow rate. So how to calculate delta M? So to calculate delta M, you see here, the product of cumulative FC So FC and the concentration different across two concentration levels, so not FC. This is delta C. Delta C. Make changes in your slide. So for example here, 0.06. So you multiply by different from 0.1 to 0.2. So meaning 0.1. So 0.06 times 0.1, that one is in percent, so you need to divide by 100%. So you will get actually in this paper the actual value for delta M is 0.0055. They round it to the nearest integer, so 0.06. But for the calculation of this value later on, 2.75, they will be using the actual value of delta M, 0.066. It is similar to this and this. They round it to nearest integer. So later, if you want to do some homework or try it, you must use the actual delta M. For example, actual delta M for this 0.066 is actually 0.0055. This, sorry, yeah. So what happened is it will affect the cumulative delta M, which is the cascade of delta M. The largest negative FFK, the last column, which actually represent the minimum fresh gas target, cascaded down the cumulative gas flow rate column FC, this column, yield the minimum discharge flow rate. Table 2 is an invisible gas cascade table, since the cumulative delta M, see here, is negative. This means that there is insufficient utility gas at the respective concentration level. So FC here, we need the pinch value from here, 5.626, added to the FC in order for the cumulative delta M to non-negative, to remove all the negative value. The amount of interval gas flow rate FFK is obtained by cumulative delta M, this column, divide by CK. So CK is this concentration, level 2 is 0.1%, minus the fresh feed concentration. For this invisible gas cascade table, the fresh feed for nitrogen is 0%. See here, level 1. So how to calculate? For example, 0.06 divided by the divide by 0.2, for example here. So don't use negative 0.06, use negative 0.0055. Divide by 0.2. Divide by 100. Yeah, times 100. Why 100? So you will get 2.75. And similar. So this value, you need to calculate the. So later, when you get the FFK, you see here, this is the highest value. This value will be used as to replace the 0. Okay. The absolute value of the largest negative 5.65. Refer to table 2. Last column is essentially the minimum fresh gas flow rate target FF. Minimum fresh gas flow rate target 5.625. This amount is cascaded down the FC column. This FC column. So cascade means 5.625 minus 0, 0. Get this value again minus 5.5 till you get the FT. To produce the minimum nitrogen discharge flow rate FT of 5.625 kilogram per second, similar FFN FT. So when you solve this problem, you start with the invisible gas cascade table first to obtain the this value, the absolute value of largest negative FFK. Then use the FFK to create another gas cascade table, the feasible gas cascade table. The minimum fresh feed and discharge flow rate identified by the GCA correspond to a reduce of 34% from the original feed and discharge flow rates of the process flow rate in table 1. So how they get the 34%? So based on figure 1, the gaseous emission, the gaseous emission is actually 8.5 kilogram per second FT. So 8.5 minus 5.625 here, divide by 8.5 again times 100, you will get the 34%. So reduction of 34% from the original feed. if we do the if we do so if we know the minimum of minimum fresh gas flow rate target instead of 8.5, actually if you reduce it to 5.625, actually in theory it will be sufficient for the for the for the process. The pinch concentration for the gas network exists at 0.4% where there is zero relative delta N. So in this case, the pinch is over here at CK level 4, 0.4%. From the limiting data in table 1, emission from the drying process, SR2, was identified as the pinch causing source for this example. So refer back to figure 1. So SR2, the source stream 2, is actually coming from drying. Yeah. Or flow rate or F2 and C2. How do you know? Because it's fall under 0.4%. 0.4%. So to achieve the minimum gas target based on the pinch, so the minimum gas target 2.875 kilogram per second of SR2, which exists between interval K and K4, should be allocated to the region above the pitch, while 2.6, because the line is over here. This is the line for pitch. So this above, below. And 2.625 of SR2 between K3 should be allocated below. So if you add 2. If you add 2.875 there, 2.875 plus 2.625 is actually equal to 5 kilogram per second, which is similar to the F2. Similar to the F2. The exact pinch causing stream distribution to meet the minimum gas target is termed as the resource allocation target. This is the second integration for oxygen. The following case study The following case study is an attempt to explore the interaction and possible site-wide integration with the process and utility section for maximum oxygen recovery. Figure 3 shows a process plant that consume a large amount of high purity oxygen, fresh oxygen here, 5% purity. High purity, oh, only 5% impurities in the fresh oxygen in its oxidation process. A relatively small portion of the oxygen is also fed to enhance the combustion system as well as for the aerobic section of the wastewater treatment plant. So from 41 kilogram per second, 4 kilogram goes as fuel, 2 kilogram as wastewater treatment plant. Actually, for wastewater and combustion doesn't need the low purity, sorry, high purity oxygen. It can always be recycled from the process. From the process here, see, 10 kilogram per second, 40% impurities discharge. This one is 5 kilogram per second with 50% impurities discharge. It should be recycled back to combustion and wastewater treatment plant, while some of it will be goes to for discharge. This. How to know? So that's why we do the cascade analysis to find the pinch point. So between this 40% and 50%, which one that can be reused? Can be reused for this case. Can be reused or recycled. The source of oxygen emitted from the oxygen consuming processes are still of good quality and should therefore be reused and recycled to reduce the fresh oxygen intake. Like what I said, from the discharge here should be recycled back to this source. Limiting data for all oxygen sink and source are given in table 4. Note that since GCA is able to handle impure fresh feed, the 5% purities in fresh oxygen supply should not pose any problem in getting accurate minimum gas flow rate target. In this case, refer back to figure 3. The gassing is coming to process 1, inlet for process 1 at 25 kilogram per second, inlet for process 2, not inlet as a fuel for combustion, and source of oxygen for aerobic treatment in wastewater treatment. This is the concentration. This concentration is referred to how much impurities, the maximum impurities that the process or the sink can limit. So for the source, we have a 2 based on figure 3. We have from process 1 and process 2. Oh, okay. So at the moment, you have learned about how to actually calculate the gas cascade table. You can refer to the nitrogen integration and which specify the gas cascade analysis technique, how to calculate FC delta M. So you may start now. You start with invisible gas cascade. Invisible gas cascade analysis with FC is equal to 0. Then you do the cascade. You do delta M. Delta M is actually FC times delta C. And do the cumulative delta M. Calculate the interval fresh gas flow rate. Then you will determine the highest negative value, which will be used as the new FC. Not the new FC. Yeah, the new FC for feasible gas cascade table. So you have two tables. Try first, then later we discuss a bit. If you have any question. So how to start? Check the limiting data. So you have 1, 2, 3, 4, 6 level. Oh, sorry, 6 stream equal to 6 level. So after that, you need to rearrange the strip in ascending order from low to high concentration. Okay, see, from low to high, so 5. You have 210 and 265. So that one you can combine. Meaning for 10 1%, yeah, the total flow rate for sig is the 25 plus 10. So we continue. One more time. So for the feasible cascade table, we've done the fit the fresh oxygen supply based on the DCT or FF, especially 30 kilograms per second. So how you get 30 kilograms per second? The one is based on the infeasible gas cascade table. You may refer to table 2 for nitrogen. So actually the difference between feasible and infeasible, they calculate the interval fresh gas flow rate, FFK. So that FFK, the largest negative value, will tell you what is the fresh gas supply, or in this case, fresh oxygen supply, to be used in the feasible gas cascade table. So, okay, we continue. Fully you try it. Normally it takes about 15 minutes like that to prepare the table. Once you're familiar with it, I think 10 minutes is enough. Okay. The gas cascade table for this case study, table 5, this is for oxygen integration. So they didn't show you the feasible, how they get the value 30 kilograms per second here. That one you need to do the invisible starting from FC equal to 0. The GCT for this case study, if a fresh oxygen supply FF and discharge FT, target at 30 kilograms second and 4 kilograms second. How they get 4? Actually, they do cascade 30 minus 0, 30, 30 minus 35, minus 5, minus 5 plus 10, 5, until they get FT. This corresponds to a fresh oxygen reduction of 27% and a discharge gas reduction of 73% compared to this, as compared to the best case system shown in 2. So how they get 27% of reduction for fresh oxygen? Actually, see here, they have already calculated or determined the fresh oxygen supply on the cascade table is at 30. So the minimum is only 30 for this process. No need to supply up to 41 kilograms. So 41 minus 30 over 31 times 100 is 27% reduction. While this charge here is actually 15. So in this table, the discharge is targeted at 4 kilograms per second only, meaning some one of these actually 40%. See, so one of these effluent output in process 1 process 2 will be recycled and reused for combustion and wastewater treatment plant. Yeah, the pinch here is 40%. So meaning 40% for process 1 here will be used for recycle and reuse. Meanwhile, 50% this one is, so this line refer to the pinch. So above the pinch is the -5. Here -5. Below the pinch is 5. It's okay. They will. So 5%. 5. Later there will be this kind of description or revised flowchart how they do the recycling, stream recycle and reuse. Network design. This section reviews the design technique for a utility gas network. Note that alternative technique for water network design may also be applied in combination with the flow rate target and pinch points established using the GCA technique. The pinch concentration identified in the targeting stage play an important role in designing a network for maximum gas reuse. So what we have done so far is to target or to identify the pinch point. And the pinch divide the network into two design regions. The region above the pinch, those and those below the pinch for problem involving a single pinch. Later on, we will have multiple pinch, just to show you multiple pinch. In the region above the pinch, cumulative impurity load surplus is in mass balance with load deficit. On the other hand, there is always excess impurity load in the region below the pinch. So the region above the pinch is therefore controlling the overall gas flow rate balance in the network. It's the most constrained part of the network. Normally for below the pinch, it hardly get recycled. Why? Because the impurities is high, and then higher than the pinch concentration. Following the observed observation in designing a gas network, gas source above the pinch, including the external gas supply. So external gas supplies here refer to the fresh feed, must not be fed to a gas sink below the pinch, of course. Yeah. You don't supply the fresh feed to gas sink below the pinch. Because the concentration is high, you just normally just discharge. Violating this rule will result in higher gas flow, higher fresh gas flow. This rule also applies during mixing of different gas sources belonging to the different pinch region. The pinch causing streams that exist at the pinch concentration is, however, an exception to this rule. We call that part of the pinch causing stream belong to the region above the pinch, while the remaining belong to the region below the pinch. This second statement you can refer to the one that we learned last week or last week. Meaning how much fraction of the stream on the pitch goes for recycle or reuse, and some fraction of it will go to the below the pinch, meaning will be discharged. To maintain steady state operation of the gas consuming processes, we need to maintain a uniform mass flow rate and concentration at the inlet stream of the gas consuming process. So here we need to maintain a uniform mass flow rate and concentration at the inlet stream of the gas consuming process. Unlike water, it can be manipulated. The flowing guideline can be used to design the network, supposing flow rate, total FSR, SSR is equal to source. Flow rate between source and sink is equal to flow rate of sink. So gas content FSR times CSR. CSR is referred to concentration of source is equal to flow rate of sink times concentration of sink. For source, FSR equal to question 2 and 3 are constraint or limit representing the flow rate and the gas content required by a sink. Equation 4 states that the flow rate of source I to be fed to sink J is limited by the availability of sink J. Any gas from a source that is not fed to sink will leave as a discharge stream. The gas network, for example 1 and 2, design using the above formulation is shown in figure 2 and 5, figure 4 and 5. This is a revised process flow diagram. For example, for example 2, the student integration, you can see the FF is reduced from 41 to 30 already. So from 30 kilogram per second with 5% increase. 21.53 goes to process 1, 0.57 kilogram per second goes to process 2. And from process 1, which is the pinch point, so meaning it will be recycled and reused. For this case, it is recycled for process 1 and process 2. So 21.43 here plus 3.57 is equal to 25, which is the requirement for process 1. If you refer back to figure 4, sorry, figure 3, yeah. Process 1 require 25 kilograms per second. So meaning 25.43, 150 complement by the recycle 3.57. So both 3.57 kilograms per second and 1.43 kilograms per second. The total is 5. So 5%, sorry, 5 kilograms per second from 10 kilograms per second will be recycled. The rest will be, so here will be reused for combustion and waste treatment plant. So both combustion and waste treatment plant require combustion require 4 kg, while aerobic treatment require 2 kg. So 1 kg coming from process 1, another 1 kg is coming from process 2. And the discharge is 4 kg, so 1 kg goes to aerobic. So like that. Noted during the design stage, the gas network should be designed independently. For the individual pinch region, this is to avoid the gas source from being fed to the sink in different design region, as well as any inappropriate mixing of gas source within region, particularly in multiple pinch or how about figure 4 for the process nitrogen? So in this case, refer back to table 3. So pinch occurs at concentration 0.4%. So above the pinch is 2, the flow rate for nitrogen supply is 2.875. And while the flow rate below the pinch is 2.625 kilograms per second. So from here, from drying, so the pinch occur at drying. How do you know? You can refer back to table 1 and table 3. So table 3, it happened at concentration 0.4%, which is fall under gas source 2, stream 2 for drying 0.6. So meaning it happened here. So what happened is, you see here, the gas is actually recycled recycle back to drying and reuse for coating. How much goes to coating? 1.5 kg, 0.4%. And reuse is 1.375 goes here, plus fresh feed of 4.125. Here the fresh feed is 1.5 plus 1.5. There's a reduction in the fresh feed nitrogen in this case. So 1.5 plus 1.5 plus 4.125 here, 1.5 plus 4.125 here, FFF and FF for coating, fresh feed for drying. If you add it, it is actually equal to FD, because in table 3, FD is equal to FF. FD is a discharge, minimum discharge, which is 5.625. FF is a fresh gas supply, for in this case, fresh nitrogen supply at 5.625 million per second. So that is for FF. So 1.5 here, 1.5 plus 1.375, F2, F2 1, F2 2. If you add this value, it's actually equal to 2.875, which is the value for above the pinch. Meanwhile, for below the pinch, you need to add 1.375 here. 1.375 here and 4.125. Once you add it, then 5.5 minus 1.5 and 1.375 is actually equal to 2.625, which is the value for FC below the pitch. So this is the revised PFT after they conduct the network design. Not also that many network design options may result as the number of casing and source increase. Designer can always impose other constraints on network design, such as forbidden or forced connection due to safety question. Okay. So 10-minute exercise. The task is to identify the value above and below pinch in figure 5.6 and locate the string. How to do? You need to refer back to table 3 for figure 4, process for the game of nitrogen here, and table 5 for process oxygen integration. Once you locate the pinch, you can see what is the stream here, and confirm that the value above and below the pinch for these two process is actually similar to table 3 and table 5. Convene at 140. After that is about hydrogen integration. This one is interesting, where they put membrane, they purify the gas and compare two methods of purification. So to identify the value, we have to have the grade. Example is oxygen integration refer to table B5. In table B5, the pinch occur at 40%. The FC of the pinch is -5 kg per second. Below the pinch is 5 kg per second as well. 50%. So here divided into 5, 5, and 5 for a second, 5 for reduce from process 1. Which means which is exactly is confirming that flow rate above the pitch, minimum gas target above the pitch, and for process 2 at 15%, which is below the pitch, it goes straight to the discharge. 1% will goes to the aerobic. Why it can be recycled to the aerobic water treatment plant? Because the maximum or limiting concentration for wastewater treatment here is 55%. It requires maximum oxygen fit with impurities up to 65%. But the impurities from process 2 is only 50%. That's why it can be recycled and the rest goes for discharge. How about recycle? This one is reuse. Sorry, this is reuse. This is a recycle. Okay, recycle for process 1. For process 1 and process 2, the inlet for process 1 and process 2 is actually 10%. So 40% here is mixed with the 5% pure oxygen. 5% pure oxygen. So when it mixes, the concentration might be reduced to 10%. How about this figure 4 dimension? So below the pinch, the pinch occurs here at 0.4%. So what happened? The pinch, they reuse and recycle the stream. They reuse for drying, recycle for cooking. So accumulation or total up to up F21 M22 here is actually um, referred to the flow rate of the pinch, while if here F22 plus FF is cycle back, right? So this plus this, we get 5.5 kilogram per 5.5 kilogram per second, which is the, if you refer back to figure 1 before the revision of PFD, for drying, the effluent is actually, the exhaust gas is actually 5.5 kilograms per second, which is tallied with F22 plus 4.125. It's actually equal to 5.5. So this charge here, this stream, is actually 5.5. If you minus 1.5 and 1.375, the remaining is here is 2.625. Well, below the pinch, and anything below the pinch normally get discharged. How do you know? Back to the thing we last week. Anything below the pinch you can discharge. For stream at pinch, you can discharge and reuse or recycle it. For above the pinch, that one is totally reuse and recycle. Okay, we continue. Third one, hydrogen integration. Mm, okay. Since hydrogen is a valuable utility gas in crude oil refineries and petrochemical plants, hydrogen reuse and recycle really has been the subject of extensive research. Figure 6 shows a hydrogen network case study where the existing fresh hydrogen consumption is reported at 277.2 mole per second here. There are 4 hydrogen consuming processes in this case study, which consists of hydrocracker in HCU, HCU, naphtha hydrotreater NHT, cracked naphtha hydrotreater CNHT, and diesel hydrotreater GHT. There are 2 beside fresh. This is important, meaning fresh hydrogen supply at 5% impurities. There are 2 hydrogen producing facilities in this network, which is the catalytic reforming unit CRU and stream reforming unit SRUs. And how much? 623 kilo mole per second. This one is 415 mole per second. The impurities is 7%. This one is quite high, 20%. A fresh hydrogen supply having 5% purity 7 for this person. Limiting data for all hydrogen sources in SIG are shown in table 6. Note that the limiting data for a hydrogen network cannot be directly extracted from the process product such as that in figure 6. Figure 6 just now, I show you. The detailed procedure to extract limiting data is presented. So they didn't specify how they not that the limiting data on hydrogen cannot be this one. So the value here is actually calculated as well. They didn't specify in this paper, but they did give a reference. Reference. The reference is in the book. Reference number 24. Analysis of refinery hydrogen distribution system by Alves and Towler 2000. So we have 1, 2, 3, 4 gas C, HCU, NHT, C, NHT, and DHT. The gas source is HCU. All the four C plus SRU and CRU. So SRU or CRU is actually a hydrogen facility, hydrogen producing facilities in this network. The result of GCA gas cascade analysis shown in table 7. Table 7 shows the minimum fresh hydrogen target F and discharge flow rate FD at 168.82 mole per second, 102.2 mole per second. Here, this way. But this is F at FD. So how they come about this value? Actually, they prepare the invisible gas cascade table. So from there you can get the interval fresh gas flow rate or FFK, the the most negative value to be the new fresh feed flow rate here. The the GCT identifies the CNHT. Okay, CNHT is the pitch causing stream wave at zero, yeah. This is pitch. From which 354.88 mole per second, this value. So, where is it? Here, okay. So 354.888 here, this value is the above the pitch, refer to this blue line. So FD, the minimum discharge flow rate, is also the above the pitch region. To further reduce, so at level K, 30% here is referred to based on this table 6, 30% here, CNHT, refer to the blue line. So at this line, this is the pinch. CNHT refer back to figure 6 is, yeah, over here. The last unit of before goes to flow. So that is the minimum. So at this stage, the minimum required is 268. If you refer back to this value, sorry, to this figure, the fresh hydrogen supply is at 277. Okay, so 277 into minus 267. So the reduction is only 3%. So it will require further reduction of fresh hydrogen intake. In this case, it's not sufficient. So how to reduce it? We need to purify the stream. To further reduce fresh hydrogen intake, hydrogen sources can be partially treated for reuse. Cycle in the hydrogen seeds. Appropriate placement of hydrogen purifier. Hydrogen purifier manipulate the properties of hydrogen stream to match the desired properties of hydrogen fields. Common hydrogen purifiers include pressure swing adsorption, PSA, membrane separation, and cryogenic separation. The hydrogen purification unit typically separate single hydrogen feed stream into two product streams. One with a lower impurity concentration than that of the other. But for water, this is talking about purification. In contrast to water regeneration unit that normally produce a single product stream, yeah, the hydrogen purification unit typically separates single hydrogen stream into two product streams, one with lower impurities than that of the other. A low impurity product stream can either be reused in another hydrogen consuming process or cycled to the same process. A high impurity byproduct stream is either purged or used as fuel. In the context of an overall network, hydrogen peroxide may be placed above, across, and below the pinch, with purification across the pinch being the best option. So in this case, purification across the pinch. When dealing with purifier placement, assessment of the impact of changes involve repetitive revision of the flow rate target and pinch relocation. So based on this statement, the fourth statement, it is easier to use GCA for any changes rather than use limiting composite curve or graphical method. Given a gas separation membrane with a hydrogen recovery of 95%, one possible option is to purify the portion of the pinch closing stream. At the moment we choose pinch, as the purification stream. The pinch processing stream lies below the pinch at 30% or equal to 102.52 mole second to a product stream at 2% impurities. At the moment, okay, they choose stream below the pinch. Not sure how much the percentage, but more than 30% concentration on impurities. From a turbulent calculation, the flow rate of this high quality permeate stream is 69.57 mole per second. So 69.57 mole is 2% impurities. Better than the fresh hydrogen feed. Fresh hydrogen feed is only 5%. 5%. This is better. The flow rate and impurities concentration for the dented stream are 32.95 mole per second and 89.11% purities. So the clean gas, after they purify it, the concentration reduced from something 13%, sure, but they didn't say, below to 2%, while the remaining is retented. Adding these two, you can see here in the tables 8, 69.6 is the premium at 2%, so goes to the highest level of GCT table, while the retented fall up to 89.11%, very high. Adding these two new hydrogen sources at their respective concentration level yield a new GCT as shown in table 8. So new GCT means you need to calculate again Fi minus Fj, then Fc, and so on. If you see here, the pinch is at the similar place. Yeah. Similar place. Similar place. Wait, we check. Not similar. Although it's at the end, not similar. And 3.7%. Note that the permeate stream from membrane separation at 2% purity is now much cleaner than the fresh hydrogen supply. 5% impurity and is located at the highest concentration level of the GCT, this one. Hence, the fresh feed and discharge flow rate of the network are now reduced to 196.8 and 30.475. If you refer back to the figure 6, the requirement of fresh oxygen supply, hydrogen supply is 277.2. Now it reduced to 196.8. It's a lot. Reduction to sensible minus 196. 29% of reduction of the minimum fresh hydrogen fluoride. Okay. Note also that the pinch concentration increases to the membrane retentate concentration of 89.11 moles. If you see here, the FD, this is FD, is 30.475. And the actual flow chart from figure 6, the amount of discharge is actually 110, 110.9 goes to fuel. They said in this before this, so excess oxygen is actually will not be discharged. It can be reused as a fuel. So how much before revision, before the installment, before they install purifier, is actually 110 goes to fuel. Now it's reduced to 30. This is the impact of purifying the stream for recycle only. Then, okay, another method of hydrogen purifier is PSA. So PSA is stand for pressure swing adsorption. With the hydrogen recovery value of 90%. For membrane is 95%. And capability to purify the hydrogen stream up to 0.1%. You see here, membrane, the recovery value is high, but the impurity, so the purification only up to 2%. PSA is better, 0.1%. So from material balance, this is based on stream below the page, refer to table 7. FT, actually FT, go to 1 or 2. One of from material balance calculation, one obtained the product residue flow rate of 64.35, and the residue is 37.87. With the residue stream practice concentration at 81%. So for membrane, for regeneration with membrane, the impurities, the residue, or not residue, for membrane is retentate. Retentate is 89%. This one only 81%. So resetting target using GCA technique gave reduced fresh hydrogen flow rate of 200 mole per second. This corresponds to a reduced discharge flow rate of 33.711 mole per second. TCT for this option is shown in table 9. So minimum discharge is actually increased to 33.7, while the fresh supply is actually 200. Yeah, surprisingly, despite the very low concentration of 0.1 mole percent. So which one that we choose? Yeah, we choose membrane. Note that in this PSA, in this case, the PSA has also purified the hydrogen source to a higher level relative to the fresh hydrogen supply, of course, at 0.1% compared to fresh supply is 5%. We can now conclude that gas separation membrane play a more important role in using the fresh hydrogen target in this hydrogen group compared to PSA. This is due to the fact that a membrane with a higher recovery at 95% compared to PSA with recovery of 90% generate an additional amount of hydrogen from the region of excess hydrogen below the pinch to the region of hydrogen deficit above the pinch. However, one should note that a purifier that gives a higher recovery may not necessarily be better. Yes, for the second example after this, next example after this, about multi-pinch problem. A purifier that produces a product stream at higher purity, PSA in this case, may sometimes be better selection in using the overall flow rate of the gas network. We'll examine this situation in the multiple pinch problem that follows. So table 10 shows the hydrogen source and sink data for example 4. This is example 4. This is on the paper by Prof. Dominic Fu. There are 6 hydrogen sink and 7 hydrogen source in this network. So 6 sink, 7 source. The fresh hydrogen supply in this case has an impurity concentration of 0.1%, which is very, very low. Here, first one. Using GCA, the minimum fresh supply and discharge flow rate are found to be under 25, and FT is 90.96. This is a typical multiple pinch problem. 2 pinches are observed in the GCT. You can see here the dua pinch. This is a multiple pinch at impurity concentration of 1.7 and 5%. Following the terminology in the water network, the pinch concentration at the lower impurity concentration of 1.7 is designated as the limiting pinch, the pinch that influences the overall gas flow rate when any process changes take place. So meaning in the infeasible GCT for this example 4, the FFK value is actually here. Yeah. 1 to 5.21. How they come about with 20? Actually, they do the cascade here. See cascade 0.068 minus 0.068. like this. Then here is middle number, input second 0. In problem involving multiple pinches, more than 2 design regions may exist. For example, for the three distinct region exists. Sorry, dua, tiga. Due to the existence of a limiting pinch at 1.7%. So for 1.7%, you actually have two sources, source 6 and source 1. See the concentration, similar. And a secondary pinch at 5%. Utilizing the GCA technique, one can quickly define the pinch causing stream and exact hydrogen limitation for the hydrogen source in each of the design region. So from the GCA technique, meaning table 11 here, actually we can identify already which level is the pinch. Another way to verify it is to use the network design. Possible one of the network design procedure describe one of the possible network design that achieve the variables established network target is shown in this table. So SK here refer to the same source stream 1. The number here is referred to the stream number. Similar as one is the source. Identification of the wrong pinch point will result in missed opportunity during hydrogen network debottlenecking. So when you choose the pinch for multiple pinch, so choose the pinch with the lowest concentration. This is particularly particularly important for a problem involving multiple pinches, where the region above the limiting pinches is the most constrained part of the network. The debottlenecking strategy will only beneficial when the hydrogen source flow rate is increased above the limiting pinch. Alternatively, decreasing the need of hydrogen sink in the region above the limiting pinch will also achieve the debottlenecking. Given the same hydrogen purifier in example 3, so the first case is regeneration with membrane. We can now determine the appropriate selection of purifier that will reduce the overall hydrogen flow rate of the network. GCT for purifying the hydrogen source using a gas separation membrane with the hydrogen gravity of 95% and producing a permit with 2% impurities is shown in table 12. So in this case, 2%. In this case, 2% is here. It's not at the top of the table. Level 4. See, so the permit is the level 8. So when you introduce two values now, you need to recalculate. Not that though, the secondary pinch pretty at 5% have been removed. There's no secondary pinch now, only one. The minimum flow rate target for this option are the same as before, regeneration. So see here, after using regeneration with membrane, is actually similar. The pinch point is actually at 1.7 as well. So therefore, there's no benefit is obtained by adding this new membrane separation unit. So it's not enough. The purity by membrane for hydrogen for this example. It requires something better, such as pressure swing adsorption. Okay. This is due to the fact that the overall hydrogen flow rate target are controlled by the most constant part of the network, the region above the limiting pinch. So this is the region above the pinch. Hence, the purifier network product streams must achieve an impurity concentration lower than the limiting concentration before the fresh hydrogen element can be reduced. So meaning you need something that can purify better than 1.7%. At the moment, if we choose membrane, the purity is only up to 2%. Another hydrogen purifier in example 3 that was used for evaluation was the pressure swing adsorption unit with hydrogen recovery of 90%. Resulting residue stream at 52.43% purity and the product stream contains 0.1% purity. Here, regeneration with PSA at this level, 0.1%, which was lower than the limiting pinch. Limiting pinch before this is at 1.7%. Resetting target using GCA gave a reduced fresh hydrogen target of 54.23 here, the pitch, and a discharge target of 19.98 mole per second. So the fresh minimum, so the fresh supply of hydrogen for this multi-pinch problem is at 120 mole. Yeah, 120 mole. With the introduction of with the introduction of PSA, the FF here, minimum fresh flow rate, is actually reduced to 54.23%. Sorry, mole per second. If you see, if you use membrane before, it's actually increased from 120. You need extra 5.21 mole per second. That's why membrane in this case there's no benefit except for adding cost. And the discharge target for membrane is 90.96. This one is 19.98. Wow, very low. So this is the case where PSA or very low concentration, very purified stream is required for the pinch. Because the allocation of hydrogen source within the whole network, the original limiting and secondary pinches disappeared. Yeah. while a new pinch emerged at the residue stream concentration of 52.43, not percent, but mole percent. Yeah. Hence, we can conclude that PSA play a more important role in reducing the overall hydrogen target in this network as compared to a gas separation membrane by purifying the hydrogen source in the region of excess hydrogen, so below the secondary pinch. PSA supply an extra amount of hydrogen to the region of hydrogen deficit above the primitive pinch. So, so far, we have done the cascade analysis tool for targeting the minimum flow rate for water and property-based network has been extended to utility gas network. For this, you learn about how to use cascade analysis for water network. This is example for gas. Last week, yeah, I saw an example for gas, but based on the time-based method. This is stream-based method. We learn about nitrogen, oxygen, and hydrogen pinch in this topic. The gas cascade analysis enable quick and accurate identification of the minimum flow rate target based on location and the source allocation target for a liquidity gas network. Yes, just by calculating, creating the gas cascade table, at least two gas cascade table is required before you can get the pinch point. Appropriate selection of gas purification technique can be systematically assessed using the GCA. So, besides, this is case for gas. So it is limited in terms of method to purify the gas. The cheapest one, I think, is using activated carbon, maybe, to improve the purity. If you have a few selection of method, I believe using cascade analysis is the best one to do the comparison. And I think that's all for my part. And so far, since week one, we've learned about introduction for mass speech analysis, some introduction of it, to do mass speech analysis. So mass speech is different from energy and heat covered by Dr. Asrul and Dr. Hari. This is mass speech analysis. Although the method is similar, composite curve, then you learn about sink source diagram and cascade. Similar method, but the way it choose the stream is different. For example, in heat integration or heat pitch analysis, we are required to calculate the enthalpy for the stream, not the flow rate of it, but the enthalpy in kilojoule per mole or kilojoule per second, depends. Then in this case, for water is flow rate. For gas, you require both water and gas is require the purity flow rate of it. And you will have learn about how to choose which one to reuse, recycle, and for how much pinch stream for pinch can be reused and recycled. That one you need to calculate that. theta. There's an equation involved, similar for gas and water, as well. What application for it? There are 4 applications now. One is for last week for methane. This week is for nitrogen, oxygen, and hydrogen. So just a bit about multiple things. So I think if you have any question, you can raise it now. For final exam, for final exam, the tip is you need to learn about cascade analysis and posit curve. I have 2 questions. One is essay, another one is calculation based. Still got time. Okay, so if there is no further question,
Doctor,
I think everyone has checked in. Okay. That's good.
doctor,
Uh,
doctor.
yeah. You have question?
Yeah, once again, what is your tips for the exam just now?
Oh, the tip for exam, I have 2 questions. First question is about pinch analysis generally, but the one is essay based. Then the second question is calculation. You need to learn how to do cascade analysis and composite curve. That's
Okay.
both is I think 25 marks. Another question is from Dr. Asron.
Okay.
Okay. So, anything else? The best we can conclude the session early. 15 minutes early. So next week I think Dr. Fari cover.
Mm.
Okay. Thank you. Is it okay?
Okay. Okay. Thank you, doctor.
So thank you all. If possible, we meet later. We can meet during your graduation.
Okay.
Jumpa lagi.